My name is Stephanie Bernard. I'm a PhD student at the University of Melbourne, and I'm just going to talk to you today a little bit about what I do as a PhD student, and I'm going to talk to you about our solar system and how we can find planets around other stars apart from our own sun. So a little bit about me. So as I said, I'm a PhD student at the University of Melbourne. I grew up in Newcastle in New South Wales, which is at the top right of the screen. When I was in primary school, I was really interested in maths and science, and especially in astronomy. So I wanted to know, what are all the stars out in the sky? We can see some planets in our sky, but also kind of more further afield, are there other galaxies? What do they look like? What sort of stars do they have? Is there life out there? All these sort of things. So I was lucky enough when I was in primary school to go to Parkes, to the radio telescope there, which isn't shown on this map, it's a bit further north. And there's a really, really big radio telescope. It's 64 meters across. And that was when I really decided I want to do astronomy. I think this is really, really cool. So when I was in high school, I moved to Melbourne. And then when I finished high school, I went to university and I studied physics. And so physics is kind of how we look at the universe as a whole. So we want to look at what are the fundamental properties of the universe. So what are all the atoms that are in our bodies, all of the electrons that give us electricity, how do they work, what's happening with them, and kind of as we go out into the universe, we want to know what are the laws that govern how everything in the universe happens, like gravity, electromagnetism, all these sort of things. So I thought physics was really cool at university, and I kept studying. I did a master's, which is like a kind of higher level undergraduate degree. And then I started doing a PhD, which is where I do basically just research. So my work is on galaxies, and I'm looking at the very first galaxies that formed in the universe. So if we look at galaxies at different distances from us, what we're actually seeing is galaxies that are further away, because we have this speed of light, which is really, really fast, but space is really, really big. And we'll kind of look into this a bit later in the solar system. And so it takes time for light to reach us. So when we look at the very, very furthest things, we're actually seeing them really, really far back in time. And we can look at the first stars, which formed around 100 million years ago. They're a little bit too far for us to see with current telescopes. We can see some of the very first galaxies only 500 million years after the Big Bang. And you can see on the timeline here, from the Big Bang, which is the beginning of the universe, to now, it's been 13.7 billion years. So we're really looking at baby galaxies in that very early universe. They're really, really small, but they're really hot and interesting to look at. So, a bit closer to home, let's talk about our solar system. So, when we look at our solar system, we have a number of different, what we call bodies in it, and this is a little picture of what they all look like. So we have the sun in the center, and the sun is our closest star. And then from closest in to furthest out, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and in the very edges of the solar system, it's not a planet anymore, but we have Pluto. So when we look at the solar system, we tend to classify the planets into two different types. So we have the inner planets, which are Mercury, Venus, Earth, and Mars. And they're much smaller. You can kind of see in this image that they're really hard to see, actually. They're made of rocks. Some of them have water, like the Earth. And then as we go further out, the planets get to be a bit bigger, and they're made up of what we call gases. So they're not solid like the Earth is. They don't have a proper surface. So they're much bigger. They tend to have a lot more moons. They also have rings. So we know that Saturn, this is a little one I brought from home, has a beautiful ring system. And actually, all of the outer planets have rings. Most of them are just too faint for us to see with our eyes. So if we kind of go into a bit more detail, and we look at our sun. So our sun is our local star. It's a star like all the others in the sky. It's just really, really close to us, so we can see it really clearly. And we get a lot of light and heat from it. And actually, all the light and the heat that we get from the sun is made in the core of it. So we can't see the core. It's really, really, it's in the center of the sun. What we see is its outer atmosphere. And we know that the sun is really, really big. So it's around 100 times the diameter of the Earth, where the diameter is basically how far across it is. So if we had our sun, and we have our Earth in the very corner, you might not be able to see it, you can actually fit 100 Earths across the sun. And actually, The sun is really, really big. If you fit them all inside, you could fit 1 million Earths inside. So this is our Earth, our sun is behind me. So they're not to scale, as you can see. I've just told you that this is 100 times smaller than this. But if we had 1 million of these, we could fit them all inside the sun. So our sun is made of gases, like the outer planets, but because the sun is making its own energy on the inside, it's really, really hot. So the surface of the sun is around 5,000 degrees. And that's hot enough to to melt metals. It's actually hot enough to vaporize some metals. So you usually see metals in forms like my phone, where it's a solid. And so imagine this is just a gas. It's very, very hard to imagine, but the sun can do that. So if we want to look at whether we can have life on planets, which is something that astronomers want to know about, well, planets that are closer into the sun, they tend to be hotter because they're getting more of the light that the sun is emitting. So if we look at our closest planet into the sun, which is Mercury, I have a visual here. So this is on the screen is a video which is taken by a satellite that's orbiting Mercury. You can see that it's got lots of craters, which are kind of pock marks on its surface where rocks and asteroids have hit Mercury over the billions of years that it's been around. So Mercury is the closest planet to the sun. And actually, it gets really, really hot because it's so close. So on the surface that's facing the sun, it's around 450 degrees Celsius. It's really, really hot. And on the side that's not getting any sun, it's actually really, really cold because Mercury is too small to have an atmosphere. So Earth has an atmosphere, it's all the air we breathe, the clouds that are in the sky, all these sort of things. And that helps to regulate the temperature of the planet because the heat can travel from one side to the other. But Mercury doesn't have this. So it's both too hot on its side facing the sun, and it's too cold on the side away from the sun. So we don't think it has life at all. It just wouldn't be able to survive there. If we go a little bit further out, we might think that it's further away from the sun, so it's not getting as much light and heat, so it's probably going to be cooler. Actually, what we see is that Venus is really, really hot. It's even hotter than Mercury. And the reason for this is because it has a very, very thick atmosphere. So if you look on the left, we have a picture of Venus's surface, and you can see again some craters. You can also see some lines stretching through, which have canyons on its surface. But actually, what we usually see is the clouds on its surface. So Venus is covered in a very, very strong atmosphere. It has lots and lots of clouds, and they make these kind of patterns on its surface. And so the way that an atmosphere can keep heat in is called the greenhouse effect. So it looks like this. So we have sunlight coming in from the sun. So it comes out like this. And then when it hits Venus, the light can go through its clouds. Some of it will get reflected, it will bounce straight off, but some of it goes in past the clouds and onto the surface. When it hits the surface, the light can actually heat up the surface, and then the surface will emit some of the light. So it will send it back out into space. Because of the clouds will actually reflect this heat back onto the planet, rather than letting it all out into space like it does on Mercury. So because the clouds are really, really thick, it actually keeps most of the heat that it takes in, and so it gets really, really hot. So if you're cooking a pizza on Earth, you put it on, say, 180 degrees Celsius, it would take you about 20 minutes to get a nice crispy pizza out. But if you're cooking it on Venus, you wouldn't even have to put it into an oven. You could just have it on the surface. It would take about 9 seconds to cook. So it's really, really hot. Okay, so if we go a little bit further out, we get to our Earth, which is our favorite. And so we can see even in this picture that Earth has an atmosphere, as I mentioned. It's got lots of clouds. It's got lots of water as well. So this is our little Earth ball. We have planets in green, and we have continents in green, and we have lots and lots of water in blue. So the Earth is really covered in liquid water. That's because it's far enough away from the sun that the water doesn't just boil off into space, and it's it's close enough in that the ice doesn't immediately freeze into ice. So this is due to our atmosphere. Our atmosphere keeps the heat in. It means that firstly the water doesn't go into space, but also we don't have a very big difference between the temperature during the day and during the night. It's only around 10 degrees, if that. And so Problem is though that if we put more and more what we call greenhouse gases, which increase the amount of heat that we keep in, our Earth is going to keep warming. And this is a really bad thing because it will melt all the ice like in beautiful Antarctica down the bottom. So this is something that scientists are working on at the moment. How do we stop the Earth from warming up too much? Yeah, so if we go out into the further parts of the solar system, we get Mars. So Mars is our beautiful red neighbour. It's much smaller than the Earth. It's only around half the size of the Earth. And because it's so small, it only has a very, very thin atmosphere. So it actually can't keep liquid water. But we know that it has ice water. So actually at its poles, and we can see on this little inflatable version, we have some ice caps. And it's possible that during the past, when the sun was hotter, this ice might have been liquid. And so Mars might have had life on it at some point in the past. As we go even further out, we get into the gas giants. And so I've said that they're actually not, they don't have a solid surface that we can stand on. What we actually see is that they're really just made up of big balls of gas. So they have clouds in their atmosphere. And this is a video taken by the Voyager satellite back in the 70s. And this shows you just how much is happening in the atmosphere of Jupiter. We have big cyclones, and so this that you can see in the bottom part of the screen is actually the Great Red Spot. And this is, 2 or 3 times the size of Earth, just a huge cyclone revolving around. So the other outer planets are similar. They're made up of gases, but they have lots and lots of moons. And so actually, what we think is that most of the moons in the outer atmosphere, and Jupiter has 4 very big ones, they have a layer of ice on them because they're really, really far away from the sun. But actually under this ice, they might have these kind of underground oceans. And so it's possible in these oceans that there might be life forming, kind of bacterial, but we do see life in very, very extreme conditions on Earth, like in really, really hot places in the ocean, and also in really, really cold places, we still see life forming. So it's possible that even though Jupiter, the planet, can't actually have life, maybe its moons do. And so, yeah, so this is we're sending satellites out to Jupiter to look at both the planet and its moons. And we have to be really, really careful when we send satellites out that they actually don't hit the moons, because we don't want bacteria that might have escaped from Earth to get onto these moons, just in case there's something there that we could kill off with our nasty bacteria. So we have one more planet, well, one more body out in the solar system, and this is called Pluto. So you might have heard of Pluto as being a planet, and up until 2006 it was, but actually it's really, really small. If we put it next to the Earth, we can see that it's much, much smaller than the Earth, and actually it's only around the size of the Moon. So the New Horizons probe reached Pluto last year, and it took these beautiful pictures of its surface, which we couldn't see before because it's just so small that even with our biggest telescopes, like the Hubble Space Telescope, it was really, really hard to see, and we couldn't get any sort of idea of what it was actually like. But now we know that it's mostly made up of ice. It's got some dirt on it, which you can see in the bottom part of the planet. But we also know that in the outer solar system, there are lots and lots of bodies that are the same size as Pluto or even bigger. So if we wanted to keep Pluto as a planet, we would have to add in all these other bodies as well as some asteroids like Ceres, which is in the asteroid belt between Mars and Jupiter. And it would just get very, very complicated. You would have to learn around the names of 20 planets, which is quite a lot. Okay, so we've looked at our solar system, and we know that in the solar system, Earth definitely has life because we're here. And then it's possible that Mars in the past might have had life, maybe some moons around Jupiter or even Saturn have life. It's possible that there are planets around other stars. And so in the night sky, if we look up, we can see thousands of stars. Actually, with the naked eye, you can see 10,000 stars, but you have to be in a really, really dark place. So this photo was taken at the Anglo-Australian Telescope in New South Wales. And this is our first, what we call dark sky site in Australia. And so this means that there's very, very little what we call light pollution from, say, street lights or houses that have lights on, these sort of things. And you can see lots and lots of stars. You can also see the Milky Way, which is passing through kind of the center of the image. And so this is really our galaxy where we live. So we're part of the Milky Way, and it's made up of billions of stars. So people started to think, well, our sun is like a star, like any other, and there are billions of stars in the galaxy, so surely at least some of them have planets around them. But until the 1990s, no one had ever seen any, actually. And so in the 1990s, the first one was discovered, but it was really hard to see. And I'll tell you why it's really hard to see. So we can actually kind of get an idea of how we could look for other planets by using just our own solar system. So we have the sun, which is letting out its own light, and we have Venus, which is much smaller, and it doesn't let its own light out. The only way that we see Venus is actually the light from the sun being reflected towards us. So if we were in the center and Venus went between us, it would block off some of the light of the sun, which is actually what we see in this image. So we have the surface of the sun, and we have this little kind of hole in the surface, and that's actually Venus getting between us and the sun. This is called a transit, and it happens every couple of hundred years when the orbit of Venus is lined up with the sun. And we can actually use this idea to look for planets around other stars. So we have to be very lucky though, because if we're where my head is and the sun is here, and the planet is going around this way, I'm never going to see the planet because it's not actually blocking any of the light of the star. Whereas if it's edge on, like Venus is, then as it passes across, it will block some of the light. And so the most ambitious experiment to do this is called the Kepler telescope, which is in space. And so the Kepler telescope looks at patches of sky for a very long time. It looks at them for years and years. And it looks for, at thousands of stars at the same time, it looks for this signal, which is where the star has a particular brightness. And then as the planet goes across, the brightness of the star changes, and it changes a really small amount because, as we know, stars are very big, whereas planets are very, very small. So it's only maybe 1% or something that the brightness changes. But we can actually still see this if we look for a long enough time. And Kepler has been really, really successful. It's found thousands and thousands of planets around other stars just using this method. Most of the planets that it finds are what we call gas giants, like Jupiter or Saturn. Because these planets are bigger, they block out more of the light of the star. And we actually find them really, really close into the star, even closer than Mercury is, which isn't something that we thought would happen. We thought that planets the size of Jupiter and Saturn, they would have to form out further from the star than we see with these planets. So this is a really interesting discovery that Kepler has made. But it's so sensitive that actually it can start to find planets as small as our sun passing in front of other stars. So these are some examples. So these names are kind of, they don't really mean that much, but you can kind of see the sizes of them. And we compare them to Earth, which is on the bottom left. So you can see that actually some of them are around the same size as Earth. But what we're going to know is, okay, these planets are very small, but we don't really know what their atmosphere is like just from this method where we look at the brightness of the star. So kind of the next step in looking at what we call exoplanets, or planets around other stars, is to actually get an idea of what the atmosphere of these planets is. And with the atmosphere, we can look at things like, do they contain water? Do they contain other chemicals that we know are essential to life? So we know that plants have particular chemicals like chlorophyll, which is used to transfer carbon dioxide into energy. And so if we manage to see a planet that has some of these signs, then maybe these planets will have life around them. So just to finish up, really excitingly, just in the last couple of months, in August, we actually found that Proxima Centauri, which is the star that's closest to us, it also has a planet. And so I say that Proxima Centauri is our closest neighbor, but it's actually trillions and trillions of kilometers away. So it's not really easy to get there. If we were going, you know, kind of at the speed of our cars, it would take thousands and thousands of years to get there. But actually, there is a program called Breakthrough Starshot, which is building these very, very small robots and satellites. And actually, if you send out thousands of these small robots, they're really, really small, so you can make them go really, really fast. You can make them go around 1/3 of the speed of light. So Proxima Centauri is 4 light years away. So if we go 1/3 of the speed of light, it's going to take us around 12, 20 years to get there. So that's actually really, really fast. We're going really, really far across the universe to get to this planet, to this star, and look at what the planet looks like. So this is kind of our best chance at maybe even being able to talk to other planets. We don't think that there's any life there because the star that it's around is actually really, really small. It's smaller than our sun, and actually lets off very, very large flares. So if our sun lets off flares, then it can disrupt our electricity, it can let off harmful ultraviolet rays, which will give us diseases. So this star is actually probably not very hospitable to life, but it's really, really close, and it's a good way for us to look at other planets in our kind of immediate neighborhood, apart from the ones that are in our solar system. So that's it. Thanks. Shooting stars are actually very small, what we call meteoroids that are out in space. They're really just kind of like grains of sand, most of them. So when they hit the atmosphere, they get heated up really, really fast. And so they let off a lot of light, which is what we see as the shooting star. So because these are so small, they're literally just the size of grains of sand, most of them. They completely burn up in the atmosphere, and all of the molecules and atoms that would have made them become part of our atmosphere. So each individual one is not really going to affect our atmosphere too much, but actually we pass through tons and tons of these little grains of sand every day. So because our Earth is so big, even these tons and tons of meteorites that we pass through, they're really not affecting us too much. So yeah, they're very pretty, but they're not going to harm us at all.
So would they leave anything behind in the atmosphere when they burn up?
Yeah, I think they would leave aside whatever they're made of. So usually it's just iron and carbon and things that are already on the Earth to begin with. I think it's really interesting. I like to do research. I get to look at pictures of galaxies most of the day, which is really, really cool. And I also get to look at kind of some of the questions that we want to know. So where did galaxies like our Milky Way come from? Because the galaxies that we see in the very early universe, we think that they merge over time to become bigger and bigger, and eventually they become galaxies like our own. And also it's really, really cool to be able to take a problem and kind of figure out all the different pieces. So problem solving is a really part of being a scientist, and especially an astronomer. So if you like, doing maths and you get to kind of sit down with a maths problem and, figure out all the pieces, then that's really good. But even kind of being more creative, so thinking, okay, if I know this, how does that relate to this other thing that I've got? So being able to kind of think creatively is a really important part as well. So yeah, I get to use really big telescopes as well.
I understand you use computer programming.
Yes, definitely.
Well.
Yeah, so computer programming is a really big part of doing physics, but also most science. It's really useful to know. So learning how computers work and how we can use them to make our lives easier is really a really big part of it. So if I wanted to take, I have several gigabytes of pictures of galaxies, and I want to know how do I get the information from these gigabytes of pictures as efficiently as possible. I don't want to look at each single pixel of each image to look at what it's got in it. I want the computer to be able to look at it and say, okay, this is what you've got, this is what's interesting, let's have a bit of a further look. Yeah, so it's made of silicon, it's made of carbon, it's made of iron, it's made of lots of different metals. So all these things kind of get mixed together in the core. And our core is like the core of the sun. It's very, very dense and very, very hot. So as we go out in the Earth, we have this layer called the mantle, which is where all the magma is. And magma comes out of volcanoes, that's lava. And so all this silicon and carbon and iron and other metals, it eventually gets out onto the surface of the Earth, and then it hardens and becomes rocks. And so different types of volcanoes produce different types of rocks. And also when the continents shift apart, we get rocks forming there. And so all these are made of slightly different things depending on the time that they formed in the Earth's history, and yeah, lots of different things. But it's mostly these heavier kind of elements.
I've heard that we're actually made out of an old star, like a star.
Absolutely.
Is that true?
Yes. So in the beginning, at the Big Bang, there was only hydrogen and helium. And so these are the lightest elements. And we know that we ourselves are made of carbon, and we're made of oxygen and iron, and all these sort of things. So to get from hydrogen, we actually have to have stars, because stars are the only things in the universe that are big enough and hot enough to actually take these very light hydrogen atoms, and they fuse them together into helium. Helium can fuse into carbon, carbon can fuse into oxygen, and so we build up these heavier and heavier elements inside stars, actually. So once the star dies, it will let out all of these new elements out into the universe, and then these new elements get formed into new stars, and eventually into planets like our own. So I said that our galaxy, the Milky Way, contains billions of stars. And we think that actually most stars will have planets around them. So based on what Kepler has found around other stars, we actually think that, you know, most stars will have at least one planet and probably more. We know that our own star has 8 planets around it. So in our galaxy, there are probably tens of billions of planets. And then our galaxy isn't the only one in the universe. In the universe, there are billions and billions of galaxies. And so each of them is made up of billions of stars. So there are just a huge number of planets in the universe. And any one of them, you know, most of them are not hospitable for life. Even in our own solar system, we only know of one that definitely has life. But, you know, even if there's a very small chance, out of billions and billions of planets, billions of galaxies, you know, it's very likely that there'll be a few that will have some life on them. When I was your age, as I mentioned, I went to the Parkes Radio Telescope, and they were playing a video on quasars. And so quasars are, you know what a black hole is? It's something that's so dense that even light can't escape. So we know that every galaxy almost has a black hole in its center. So our galaxy has a black hole in its center, and that's got the same mass in it as billions of stars. So it's really, really big. Ours isn't eating anything at the moment. It's what we call passive. It's just kind of quiet and it doesn't do anything. But some galaxies, they're actually eating up gas and stars and things kind of around them, and they let out lots and lots of light. And so they had this video on how this happens, and I thought it was so cool. I was like, there's these things in the universe that are just eating up whole stars and gas, and they let out light and we can see them. And so I think that was kind of why I decided I wanted to do astronomy. Yeah, so that's a good question. So back in the 1990s when I was a kid, we did actually think that, well, you know, that it was a very plausible possibility that the Big Bang would happen and the universe expands. And then if there's enough matter in the universe, then eventually it would actually start to collapse. So gravity would take over and it would come back in and cause this big crunch. And so, of course, in this, you know, the Earth and the Sun would get crushed up as well, and then it might become a new Big Bang. So it might kind of rebound and become a new universe. So since then, we've actually discovered this thing called dark energy, which is some sort of force in the universe that's kind of pulling everything apart. So the expansion of the universe is actually accelerating. So rather than going kind of like this, where it accelerates over time, it actually starts off small, and then it goes much, much faster than we thought it was. And in this case, actually, we don't think that there's enough matter in the universe, in all the stars and galaxies, and this thing called dark matter, which is most of actually what the matter in the universe is, that actually there's not enough of this to make it kind of pull back in and become a big crunch, which is a shame because it's a nice idea about how the Big Bang happened. At the moment, we really don't know why the Big Bang happened. All that we know is that the evidence that we have strongly suggests that we had this Big Bang in the past. We don't know why. The first telescopes were made in the 1600s. So Galileo was one of the first people to use a telescope, and he discovered moons around Jupiter. Really, kind of since even the ancient Greeks, we've kind of known that space is quite large. During that time, actually, people thought that the sun and the other planets and the stars orbited around the Earth rather than the other way around, where the Earth orbits around the sun. But even then, yeah, they knew that the distance from the sun to the Earth was really large. They could work out how big the Earth was just using trigonometry, which you guys will learn in maths kind of in high school, and just using kind of shadows and how, you know, how long shadows were at different times of the day, at different times of the year. So yeah, so even 2,000 years ago, we kind of knew some of the basic things about the universe. Dark matter is this thing we don't really know what it's made of, but we can see its effects on the universe. We can see that it's only affected by gravity. It doesn't really interact with matter, like the atoms in our bodies or in stars or galaxies. But we know that when we look at galaxies, there's too much matter in them, so they're rotating faster than they should be. And we can see actually in galaxy clusters as well, the properties that they have implies that they have lots and lots of dark matter in them. So we can't see it, but we kind of can see what it does to the universe. And we have some ideas what it might be. It might actually be very small black holes. It might be, planets that we just can't see because they're very, very faint. Or it might be kind of more interesting things like what we call subatomic particles, like smaller than atoms, even the ones that make up ourselves and everything. And that's what kind of particle colliders in Europe and in the US are trying to find, actually. So they send very, very high energy protons at each other, and they look at, is there any kind of mass that they don't detect from this? Because then they think that maybe they've actually created dark matter in their colliders. My favorite planet is Saturn, because it's got these beautiful big rings, and if you get to look at it through a telescope, it actually looks like a picture. It looks like it's got this, yellow planet in the center, and it's surrounded by these beautiful rings. And actually, if you have a big enough telescope, you can see there's this gap in the rings, which is formed by some of the moons around it, and it's just very pretty. It's a bit of a mystery as well. We don't really know exactly how these rings formed. We think that they actually must still be forming as we speak. So yeah, it's a very interesting planet, I think.